All right, we're going to do some game theory. Not a lot, just enough to sort of scratch the surface, define some terms, and see a little bit about how game theory works. Um, Game theory is really a course unto itself. And while the theory is used frequently by economists, to really see in depth the way that economists use it takes a lot more time than we have. So I just want to give you some basic definitions and show you some of the basic mechanics of game theory. Um, the way that we use game theory is what's called non-cooperative game theory, where we have players who aren't necessarily cooperating with one another, who are involved in some sort of a relationship, and each one wants to come out on top. Each is a profit maximizer or a utility maximizer, depending on the context. And So let's take a look at some examples, and we'll talk about what we can learn from them. So so game theory. First of all, there are a couple of different ways to illustrate games. We can show games in extensive form, which means using a game tree. Or we can show games in what's called normal form, using a what's called a payoff matrix. So let's start off with the game, and we'll illustrate it both ways. And in this game, there are two players, and so the players are the participants in the game. And let's suppose that these players are two airlines that compete with one another, and I'll call those airlines Air Alpha and Air Beta. Okay. And in extensive form, here's what the game looks like. Well, actually, before we get to that, let me just say that when we think about games, there are a variety of ways to sort of set them up. Games can be simultaneous, or they can be sequential. So a simultaneous game is like football, where both teams move at the same time and try to hide from one another what their strategies are. And tennis is more like a sequential game where each player responds to the other player's move. And so what we'll do is we'll set up a sequential game between Air Alpha and Air Beta. And so I'm going to draw a little node here, and that node represents Air Alpha. And these two airlines, we'll say, are competing over a specific route, an airline route. And the way they're competing is sort of like Cournot duopolists. They can either provide a high volume of service or a low volume of service, a lot of seats or very few. And so Air Alpha makes its choice. It chooses high or low output. And Air Beta then responds. Okay, and so Air Beta gets the second move, and Air Beta either chooses high or low output, high or low output. And the payoff is in the form of profitability. And so if Air Alpha chooses high output and Air Beta follows with high output, the payoff will be $4,000 for air alpha and $4,000 for air beta. So air alpha has the first move and they get the first payoff. That'll be the convention we'll use. If air alpha takes high output or produces high output and air beta low, then the payoffs will be 6,000 for air alpha, 1,000 for air beta. If air alpha chooses low output and air beta high, then the payoffs will be 1,000 for air alpha and 6,000 for air beta. And if both choose the low output, then the payoffs are 3,000 and 3,000. Okay, so that's a game in extensive form. And our task is to try to find the equilibrium for the game. And the way to do that is to, we want to identify the optimal strategies for each farm or for each player. Okay. And there are different ways to find optimal strategies. The simplest way, and the one that will work here easily for us, is to use a process that's called backward induction. And the idea behind backward induction is this. The game, as we envision it, gets played from beginning to end. With backward induction, what we do is start at the end of the game and work our way back toward the beginning to understand the situation faced by each player in the game. Okay, so let's do that first for, well, we'll start with air beta since they get the last move. So for air beta, here's what they're looking at. They can say if air alpha chooses to produce a high level of output, then air beta gets a payoff of either 1,000 or 4,000. They're better off with a payoff of 4,000. So air beta's optimal response is high output, right? So if air alpha chooses high, so we're on this top branch, okay? Air beta will get a payoff of either 1,000 if it produces low, or 4,000 if it produces high. 4,000 is better, so air beta's optimal response is high. If air alpha chooses low level, so now we're on the lower branch, air beta's payoffs are either going to be 3,000 or 6,000. They preferred 6,000, and so air beta's optimal response is to produce a high level of output. And now we can see air beta's optimal response is the same regardless of what air alpha does. So we would say that air beta has a dominant strategy and that strategy is produce a high level of output. What is a dominant strategy? It's a strategy that works regardless of what the other player does, right? It always dominates the alternative being produce a low level of output. For air beta, producing a high level of output is always better, and so it's the dominant strategy, okay? Now, we've identified air beta's optimal strategy. Now let's look at air alpha as we play the game backward. They can say this: if air beta chooses a high output, then air alpha's optimal response is, well, let's see. If air beta chooses a high level of output, then we're either going to be here or here. If air beta chooses a high level of output, then air alpha can choose a high level of output and get a payoff of 4,000, or they can choose a low level of output and get a payoff of 1,000. They prefer 4,000, and so air alpha's optimal response is to produce the high level of output. Okay? If air beta chooses the low level of output, then air alpha's optimal response is, well, let's see. If air beta chooses the low level of output, then either air alpha gets a payoff of 6,000 here or 3,000 there. 6,000 if it chooses the high level of output, 3,000 if it chooses the low level of output. Okay? And so 6,000 or 3,000, they're going to prefer 6,000, so their optimal response is to produce high. And so air alpha also in this simple game has a dominant strategy, because regardless of what air beta does, whether air beta chooses high or low, air alpha always chooses a high level of output. And so in this game, each player has a dominant strategy, which means that they're always better off choosing a high level of output. And that means that this high output from both is the game's equilibrium. And this equilibrium has a specific name. It's referred to as a Nash equilibrium. And that's named for the Nobel Prize winner in economics, John Nash. Nash was actually a mathematician, not an economist. He's the person who's really credited with moving game theory from a not particularly useful tool into a very useful tool. And his insight is this Nash equilibrium. And a Nash equilibrium is the solution to many different kinds of games. And the definition of a Nash equilibrium is this. It's when it's the equilibrium that results in a game when each player's strategy is an optimal response to the opponent's optimal strategy. Okay. In this case, both players have the same optimal strategy, which is always choose high. And so each player is in fact choosing an optimal response to the opponent's optimal strategy. This definition at first seems a little bit circular, or it seems a little bit obvious. It's like a lot of things that people have won Nobel Prizes for in economics. Once you see it, it's obvious, but it takes a genius to see it. And that's what Nash was. All right, so that's our first game in extensive form. We can represent the same game in normal form. And in this case, what we'll do is this. We'll draw a payoff matrix along the side, air alpha. And so the player that gets the first move is going to go on the side in our payoff matrix. And the player that gets the second move goes up here. And each player has a choice of choosing a low level of output or a high level of output. If both choose the high level of output, the payoffs are 4,000, 4,000. If both choose a low level of output, the payoffs are 3,000, 3,000. And if they choose low and high, the payoffs are 6,000, 1,000, and 1,000, 6,000. Okay. So those are the same payoffs as what we showed before in extensive form. To find the equilibrium in normal form, what we do is this. We say, we basically go through the same process, but we're not obviously working backward because there's this game could be a sequential game or it could be a simultaneous game. It really doesn't matter. So let's do this. If air beta chooses a low level of output, what's air alpha's optimal response? Well, if air beta chooses a low level of output, then we'll be in this first column. And air alpha has payoffs of 6,000 or 3,000 available to it. They're going to prefer 6,000. So when air beta chooses a low level of output, air alpha will choose high. If air beta chooses a high level of output, air alpha is looking at payoffs of 1,000 or 4,000. They're going to prefer 4,000. And so those are air alpha's preferred responses. They're optimal responses to what air beta does. Now let's flip it around. If air alpha chooses a low level of output, air beta will have payoffs of either 3,000 or 6,000. Okay, so the first player, the player on the side here, has the first payoff. Player up here goes second, has the second payoff. So if air alpha chooses a low level of output, air beta's payoff is either 3,000 or 6,000. They're going to prefer 6,000. If air alpha chooses a high level of output, air beta's response will be either 4,000 or their payoff will be either 1,000 or 4,000. They're going to prefer 4,000. And so you can see that both players want to be here. And this is the Nash equilibrium for the game. All right, so that's the basic structure of a game. What can we do with this? We can illustrate a variety of different situations. The key to game theory, as we're doing it here, is setting the payoffs in a way that make a point or lead us to a certain understanding. Okay, so let's play a different game. Let's suppose we play the grade game. Okay, and so suppose what's happening is that you are doing a project with a partner. And we'll write this game down in normal form. And so there's you, and there's your partner. And there are different strategies you could use in working with your partner, okay? And so each of you could choose different strategies. Let's just call the strategies alpha and beta. Not exactly sure what they are. Doesn't really matter. Those are the two strategies available to you. And let's suppose the payoffs look like this. If both of you play this strategy alpha, then your grades will be B- for you and B- for your partner. If you choose strategy alpha and your partner chooses strategy beta, then the payoffs will be this. You'll get a grade of A and your partner will get a grade of C. If your partner chooses alpha and you choose beta, then you will get a grade of C and your partner will get an A. And if you both play the strategy called beta, then you will each get a B+. And so when we look at this game, we say to ourselves, well, seems like these two outcomes, AC and CA, are not really mutually beneficial. If you're just out to overwhelm your partner, well, I guess maybe you could try to get the game there. But it seems like if we look at it, that this is the outcome that is most beneficial, or at least least harmful for both players. Okay? And so it seems like this is where we would like the game to end if we have an interest in this game. All right, let's play the game and see how it's going to work. And again, we use backward induction. So we'll start here. If your partner chooses strategy alpha, which strategy will you prefer to respond with? So if your partner chooses alpha, your payoffs will either be C or B minus. You're going to prefer the B minus. And if your partner chooses beta, your payoffs will be either B plus or A. You're going to prefer A. So it looks like you have a dominant strategy of always playing alpha. What about your partner? If you choose strategy alpha, your partner will have payoffs of either B minus or C. Your partner is going to prefer B minus. And if you choose strategy beta, your partner gets a payoff of either A or B plus. Your partner prefers A. And so you can see that we never end up here. And this is actually the outcome of the game. That's the Nash equilibrium for this game. This is an example of a type of game that's referred to as a prisoner's dilemma. Okay, and the prisoner's dilemma turns up in lots of places once you know about it. It's not hard to spot, actually. Let me take a step back and explain to you why it's called the prisoner's dilemma. The original example used to illustrate this type of game involves two criminals. And the criminals commit a crime. And there's, we'll call them player A and player B. These are the two criminals. And they decide to commit a crime. And they pledge to each other that if they get caught, if they get arrested, neither will ever confess to the crime. Okay? That both of them will simply deny, and they know that that will work out best for them. And so they either deny that they had anything to do with it, or they confess to having committed the crime. Okay? And each player then has those two options, either deny or confess. Confess. So if both players deny that they had anything to do with the crime, then each will argue that each of them will be convicted of a lesser offense, and each will get 1 year in prison. Okay, so that's 1 year for each player if they both deny. If player A denies and player B confesses, then player A will get 10 years in prison and player B will be let go. If player B denies but A confesses, then A will be let go and B will get 10 years. And if both confess, each of them will get 5 years. So similar to the case above, we look at this and we say, well, clearly this is the case that is most beneficial for both players. They have agreed to deny any involvement with the crime. And as long as they both hold up their end of the argument, their end of the bargain, then this is where they'll end up. They'll each be in prison for 1 year, which is the best outcome mutually. Now let's look at this as a game and see through backward induction what the optimal strategies are. So suppose player B decides to deny any involvement. Player A will either have a payoff of, or a, will either be imprisoned for 1 year or set free. They'd prefer to be set free. If player B confesses, then player A will either get 10 years or 5 years, and clearly would prefer 5 years. What about player B? If A denies any involvement, then B will either get a year or be set free. They prefer to be set free. And if A confesses, then B will either get 10 years or 5 years. He'd prefer 5 years. This turns out then to be the Nash equilibrium for the game. Why do we end up here? The players have an agreement that they're both going to deny any involvement, and yet the game ends up here where both have confessed. What kind of a game is this? This is a game about trust, okay? If I can trust my partner to hold up his end of the bargain, then I can go ahead and play this strategy. But it's a risky strategy, okay? And the risk is that if I hold up my end of the bargain and my partner doesn't, I end up in prison for 10 years. Okay? And so if you don't have complete confidence in your partner to hold up the bargain, the Nash equilibrium, the optimal strategy for each player is to confess, and that brings us here. So what are examples of real life prisoners' dilemmas? There are a number of them. You can think about it this way. People have argued that nuclear arms present a prisoner's dilemma. For many years, the United States and the Soviet Union and Russia each had nuclear weapons. And many people have argued that the reason that each of them had weapons was because the other had weapons. We'd be much better off if neither had any nuclear weapons. But neither having a weapon means that they have to ensure that the other doesn't have a weapon. If I think you have a weapon, then my best response is to arm myself. And so both sides having no weapons is the optimal situation. But since we can't trust the others to do what's necessary to reach that, we end up with both of us arming ourselves. Other examples of prisoners' dilemmas. Think about people who arm themselves at home. Why do they do that? Because they're afraid that they may be attacked, or they may have their home broken into by someone else who is armed. If we could assure that the person who breaks in is not armed, then we'd be happy not to be armed. But since we can't assure that, we arm ourselves. Some people have argued that SUVs are an example of a prisoner's dilemma. If you get in an accident and you get hit by a vehicle that's very large, you're much more likely to suffer serious injuries. And so we'd all be better off if everybody had small vehicles, which don't inflict nearly as much damage during an accident. The problem is this: if I commit to a small vehicle, then I have to make sure that you have a small vehicle, but I have no way to do that. So if I'm concerned that you're going to have a large vehicle, even though I believe that the world would be better with everyone having small vehicles, if I think you're going to have a large vehicle, my optimal response is to arm myself with a large vehicle. These are everyday prisoners' dilemmas that come up in life. And so they're worth knowing about. And once you're aware of them, they're not very hard to spot in life. All right, I'm going to stop there. We'll come back and do a little bit more in a while.